Today we will do application of derivatives and integrals in kinematics for the motion in a straight line. So, for example, what we use is x is our displacement from the origin. The derivative of x by time is our velocity, and the derivative of velocity over time is our acceleration. So it's obviously that acceleration is the second derivative of displacement by time. So let's see an example and discuss the value. So this is the motion in a straight line. So here is our O for the origin, or 0. So from this side we have positive numbers and here the negative numbers. So if x is greater than 0, that means that some, say this is a point called P, that a particle or whatever is located to the right of the origin. It's right side of origin. If P, that's P, say 1, if P2 is on the negative side, then x is less than 0 and it's on the left of the origin. It's gone to the left. And then, so what, and when x is here, then x is 0. It means that P is at the origin. So P is at the origin, say that's position number 3. So similarly, when we have, say, for example, if it happens that somewhere around here we have, say the particle is somewhere around here, and obviously that's position, say, number 4. Say that velocity here is greater than 0. So it means, this is the right hand side, it means P is moving to the right. So P is moving to the right. If V is less than 0, that's moving to the left. So say here in the article moving to the left. So let's go further, say acceleration. So let's take a different color and say somewhere around here at P position 4, and we have that acceleration is greater than 0, which means the article is being pushed. So put double arrow, pushed to the right. And if it happens that A is less than 0, pushed to the left. So it's pushed. The word we use is pushed. So we are helping it with a push to go in that direction. So what happens when acceleration is 0? When acceleration is 0, it means the artist is no longer pushed. No longer pushed. And what happens when V is 0? When V is 0, the article has stopped. There is no velocity, no movement. So P has stopped. P has stopped. So, and we said it's at the origin. When X is 0, then it's at the origin. Alright. Let's pause it. Let's now draw a diagram of displacement in the function of time. If the diagram looks like something like this, so here we have a point where we have an initial, time is 0, therefore this point here is initial displacement. So it's obviously to the left of the origin because it's exactly 0, because here we have plus and here is plus, here is minus, here is minus 2. So initial displacement here where we have the displacement is 0, so it's at the origin. So here and here displacement is 0, so the particle is at the origin. So you have to have that reference point of origin. And now let's try to put to add interpretation for velocity. So here, if you put, for example, in this point here, we put a tangent. So we see that here velocity is greater than 0. Say at this point here, and displacement is less than 0, so which means that the particle is moving, is to the left of the origin, and it's moving to the right, moving to right, to the right hand side. Say, and that all goes until this point, when say like that, and in this point, so this one was here, and in this point here, in time, say that's not 1 second or whatever. 1 second, after 1 second, say the velocity is 0, the particle is no longer moving. So if t equals 1, we have v equals 0, no movement. And then we have the velocity going down, so v is less than 0, moving to the left. And here we know that we use the second derivative. If you remember, the second derivative points to concavity, and when it's less than 0 means concave down, which is our case. So we have here that second derivative, or the acceleration, is negative. What does it mean, the combination? What do we have now? Say at this point, say let's take a point here on the curve, and at this point in time, say, and this point of time, that's 1.5 seconds. At this point of time, t equals 1.5, we have that the displacement is greater than 0. We have that velocity is less than 0, and we have that acceleration is less than 0. So what happens is the article is moving to the left, so it's moving to the left, and it's not only that, but because its acceleration is in the same direction, it's actually is being pushed to the left, so it's speeding up. Let's mark a point here. That will be 0.5 seconds, and that point there, we have obviously that the tangent is positive. So at the point of t equals 0.5, x is greater than 0, v is greater than 0, and the acceleration is obviously, it's concavity down, so it's less than 0. So what it says, the particle is to the right of the origin, v is greater than 0, which means it's moving to the right, and the acceleration is opposite direction, therefore, and slowing down. So it's slowing down, it's moving to the right. In conclusion, we can say when V and A are the same sign, then we have speeding up follows speeding up. Speeding up, and we have V and A are different signs. We have slowing down. And at the end, let's point out to the difference between displacement as different from distance traveled. So if we have a graph like that, or velocity, and for example you have function like that, so you know that x is equals v times t, yeah. So v times t is the displacement, so it's the area covered between these, say at this point here, point this, and between point this, that we call it A and call it B. So if we look at now and put the displacement, so will be, this is negative, say A2 is negative, and this is A1 is positive, therefore the displacement would be say equals to the integral of, an integral is the area between, as we know, A and B, where you go of v of t times dt, and that in this case will be A minus A1 minus A2, because A2 is negative, so total area. So it will be, say, just a bit bigger than 0, but that's our displacement. But if we want the distance traveled, x traveled, then you will have the same integral split into 2. So here you will have a point of, say, A1, so you will have the integral. So let's move it a bit more to the right, to the left. X traveled. So x traveled displacement. X traveled is integral from a to a1 of v of t dt, then plus, and then you have the absolute value of integral from a1 to b, so that the traveled is much greater number. It's v of t dt. Therefore, x displacement is less than x traveled. And for the end, so that means basically what we do we take a1 and we add it to a2 if the a's represent positive numbers. So if a are positive numbers, because now you have one more apart from these formulas here. Apart from these formulas here, we have one more formula that will use, and that will relate. Let us derive the latest formula. dv by dt, that's our acceleration. So now we can write that as dv by dx times dx by dt. So that can be crossed out, so we just extended it. So dx by dt is v. Basically what we have, write it first, v times dv by dx. So now let's try to write this v as a derivative of something. Obviously derivative of v squared by 2 divided by 2 is by dv is v, and we have dv by dx. So now we can cancel them out, and we get d of v squared divided by 2 by dx. As we said before, the formula is used when the t is not given, the time is not given, when we have acceleration and displacements, or velocity and displacement given. That's all.